anyone tell me what is ground state in terms of energy? Do you have any idea how those two things relate? Yeah. Yes. So what do you think that means about in terms of energy? You think it's high or low? Yes. So this is the lowest possible energy level. So to be in ground state, now this ground state can differ depending on the electron, but typically for simplicity, we put ground state as the energy level closest to the nucleus that has the least amount of energy. Now, what causes electrons to rise in energy levels? Energy from an outside source. So energy from outside. Now this can be anything from light, heat, we used a flame, or it can be electricity. So when we do our lab today, we are actually using electricity to make hydrogen gas glow like a pinkish purple. It's in an enclosed glass tube. No, that's different. All right. So I talked about these electrons eventually coming back down from their excited state. What do you think initially drives their want to come back down? Why don't they just hold on to that energy? Not quite. Exactly. That's the key is their charges. What's the charge of an electron? What's at the middle of an atom? Exactly. So what happens is they're actually attracted to the nucleus. And so that's why they fall back down. So electrons are attracted to nucleus. So how do those electrons release that energy? In what form? Lights or photons, okay? Photons, which means light. Now, I know that elements have different colors, but what determines the different colors that we see? Yes, the wavelength, which is associated with what? Energy, exactly. So the color of light is determined by the amount of energy lost back to ground state. Now, we know that energy and wavelength are related. How does the amount of energy of a photon relate to its wavelength? Is it a direct or inverse relationship? Inverse. So, inverse, so it goes opposite directions. So when you have a high energy, you have a small wavelength. So what I have pictured down here is the whole electromagnetic spectrum. The only part that we see, so all the colors and all the stuff that we can see, is just this little chunk here. That's it. So it's magnified here to show the colors, but just this little chunk is all we can see out of this whole entire spectrum. Okay. So you guys have heard of radio waves. I'm sure most of you guys use Bluetooth now, but some of us don't have that luxury in our car. And then we have things all the way up like X-rays and gamma rays. Now, which are more harmful? X-rays or radio waves? X-rays. So what do you think that means about its energy? Exactly, X-rays on this side of the spectrum, this is your higher energy. And this is your lower energy type of waves. Now, what can you tell us about our wavelengths? Inverse. Okay, so on the bottom here is relative wavelength. So notice on the high energy side, it's very tiny. Where towards here, the wavelength is a lot bigger. Okay, so what we're looking at today is giving this some equations. Okay, any questions before we move on? Sweet. So we have what are called bright line spectra. So I know it sucks when you guys have it printed out in black and white. I can't print in color, but if you want to label, go ahead and write things like purple 1 or maybe darker purple. Call this blue. So it might be helpful to just write in what these colors are since they didn't show up. If you have colored pens or highlighters, that'd be a great use. This one's red. Like I said, just another purple here. Okay. Now, electrons can drop from excited states in different pathways. I briefly touched on this the other day. What that means, I'm gonna just flip back a page here in a second, is that let's say this electron goes all the way up to this level. When it's ready to come back down, it could jump here and then back down, causing 2 different photons. If it comes all the way up, it could drop here and then all the way down, or maybe it even just takes a stepwise path. So how the electron falls back down can be any combinations of falling down between the levels, which all have a different energy associated with. So the differences between all the energy levels in an atom, that's what creates these colored lines. So this energy is associated with a drop between 2 levels. So is this one, so is this one, so is this one. All right. Now, yes, there are, well, actually, I'll get into that later. Now, like I said, each drop, so pretty much I'm just highlighting kind of what these points here are saying. We're going to give this an equation. Energy is equal to H, and this is called nu. So if you guys like Pokemon, H nu. All right. So it's pretty much a fancy V. Nu? Isn't nu a Pokemon? Mew. Oh, yes, it's spelled similar. Nu, right? Isn't it? Oh, whatever. I don't know. Darn it. I was trying to be relevant. Okay. Anyway. And you, that's new. What is E, do you think? Energy. H is what we call Planck's constant. And then we have nu. This stands for the frequency. Now, this nu, the frequency, is actually equal to C over lambda. So I'm going to substitute that in for the equation. H times C over lambda. So right now I'm just substituting this. Yeah. I'm getting there. I'll get there. Yeah. Yes, that's totally okay. So C, that is the speed of light. And then lambda, that's what we've been using for wavelength. So really there's 2 kind of equations we'll use. If we have a frequency, we just use H nu. If we have a wavelength, then we'll use H times C over lambda. Okay, so. Huh? Oh, nope. Hi, Brock. So some people just do an upside down Y. I'm just a little fancy when I draw my lambda. LAMDA, I think. Lamb. Is there a B in there? I don't. Ta-da! This is what I try to draw. That sucker right there.
No, turn your computer upside down.
But why? I truly became a teacher, so I have a platform for my dad jokes and bad puns, to be honest. All right, anywho, let's get back to math, right? So, talking about these then. Underneath where these lines occur, we have these numbers, 6 to 2, 5 to 2, 4 to 2. What do you think that represents? Any ideas? Exactly. This is the color or the wavelength, the energy associated with jumping from energy level 6 to 2. So thinking about that, right now we only have 4, but I'm going to add partial 5, 6 out here. Jumping from 6 to 2, would it make sense that this has higher energy than jumping from something from 3 to 2? Yeah, right? And what do we know about higher energy? Shorter wavelength. And our shorter wavelengths belong, that's where our purples live. So purples tend to be on the bigger jumps. They have a lot of energy. And you know how I remember that? UV rays, ultraviolet rays, they're the ones that can give you, skin cancer and whatnot. They're harmful. Ultraviolet, violet's closest to that. It's the step before we get to harmful. So that's how or infrared, no biggie. That's next to red, lower energy. Anywho, I digress. So these are the different numbers. Now, why do you think there's no line dropping to the first level? There is a first level. It's what? Exactly. It's too much energy to the point, or too little energy where it's out of our visible spectrum. So we have to remember, even though this is all we can see is this tiny chunk, there might be pathways that land outside of our visible spectrum, so they don't show up. So energy emitted outside visible range. All right. I kind of want to do this just for funsies here. What? I'm going to do this. I'm going to do a calc real quick in the upper corner here. So what if I wanted to know the energy of this red bright line spectral line? So I have my energy equation as such. This is a constant. This is a constant. That means they're always the same number. All you have to do is plug in your wavelength. It's that simple. But what do we always have to be careful for in science? What comes after the number? Units. Yes, exactly. So that's the biggest thing, is making sure that your units match. So we'll practice this. We're going to test out your math skills during your lab, but I just kind of want to talk to you about that. Okay. All right. Moving on to 1.4 electron configuration. Some people like this, some people don't. That's fine. We'll get through it. Okay. So there are 4 types of ways that we can discuss our electron configuration. What an electron configuration is a way to describe where the placement of all of our electrons are in an atom. So the 4 types are shell. And then this has to do with the principal energy levels. You guys are going to get sick of principal energy levels. Oops, I just wrote the wrong principal. And I'm going to abbreviate that as capital P-E-L. If you guys haven't picked up on this yet, I love abbreviations. We have to talk about subshell config or sublevels. These are within principal energy levels. Then we have orbitals, which are within sublevels. And lastly, we have what are called Lewis dot. And these only look at valence electrons. Does anyone know what a valence electron is?
Outermost.
Exactly. So this deals with the valence or outermost electrons. So we don't care about the ones that are hanging out on the inside. All right, so let's first talk about shell configuration. So we need to kind of figure out, okay, we have these principal energy levels. These are our shells. So when we talk about energy levels, when I talk about how many rings are around the nucleus, there's 1, 2, 3, 4. Guess what? Those are our principal energy levels. Okay. So when we call these n equals 1, n equals 2, n equals 3, n equals 4, that's typically how they write principal energy levels. So in our case for potassium, we have 4. So we have 4 shells, which I can talk about. And you guys have discussed, you know, in previous classes, how many electrons each of these shells can hold. And so we are going to go through that real quick here. So in your first principal energy level, you can only hold 2 electrons. This number grows as you get further away from the nucleus. The next is 8. 3 is 18. And lastly, 32. So how you write shell configuration, if we think about, we have the first, second, third. Now this could keep going depending on the element, but in our case, how many energy levels does potassium have? 4. So we're going to write this 4 terms. So what you're doing is just writing the number of electrons in those energy levels with dashes in between. So starting from first to fourth. So potassium has how many electrons? 19. Remember, it'll be the same as the atomic number. So we have to distribute 19 electrons, and they fill from the inside out. It's that simple. So if the first can hold 2, oh wait, so why did I? Oh shoot. Okay. Do I want to get into that?
Yes, you do. Do it.
Okay, it'll be, yeah, we'll get there eventually. Okay, so in the first level, we can fill 2. The next one can hold 8. And at this point, we're still not at 19. Now, what's weird is you guys are going to want to just throw 9 into the third energy level, but that's actually not the case. So this is what I mean by getting into it. Now, it has to do with the sublevels, because sublevels can only hold so much, and there's a specific fill order that we're going to talk about. So this isn't something that I necessarily expect you to know right now walking away, because we haven't talked about the specific fill level. So that's why I was debating getting into this right now, but I just wanted to show you kind of how you would represent it. So no, for example, if you were given a diagram like this, you could just count. All right, how many are on the first string? 2. All right, put 2. Next string, 1, 2, 3, 4, 5, 6, 7, 8. You'll notice that there's 8 around the third and just 1 in the last. Like I said, we'll talk about why that is here in a second. Okay, so I'm just gonna make a note here because I'm not just gonna leave you in the dark, but not all in third principal energy level, because I do B/C sublevels. Okay. Now we're going to talk about sublevel configuration. Okay. So next page. The key here, except there tends to be exceptions. This is why some people hate electron configurations. But for the most part, one sublevel must fill completely before the next. So this is not the rule for principal energy levels, but it is for sublevels. So we start with our principal energy levels. Inside those, we have orbitals, or sublevels. And so those consist of S, P, D, and F orbitals. Have you guys heard of those before? So this is brand new concept. I'm trying to test the water to see how far we've got. So we haven't heard of S, P, D, or F. We have. I'm getting mixed signals. Some of us have. Okay, so sublevels. Okay, don't worry, we'll cover it. So now these sublevels, pretty much what they are is specific shapes that were predicted where the electrons live, and they can hold so many. So the maximum capacity for each sublevel will stay the same no matter what principal energy level they're in. So see how we have an S sublevel that holds 2. This exists in principal energy level 1. So on the bottom here, what we're going to write in is max electrons per sublevel. In our case, it's 2 electrons for S. Our p orbitals can hold 6 electrons. D will hold 10. And F will hold 14. So again, following this trend that I'm going to outline on the table. So principal energy level 1, that can only hold an S sublevel, which is why you can only hold 2 electrons in principal energy level 1. So this 2, so this is the hardest part about this unit, is getting the difference between energy levels, sublevels, orbitals down. I'm just going to throw that out there now, okay? So we have our energy level that inside consists of sublevels. So in this case, I'm just going to call this a sphere, because that's what the shape of an S orbital or S sublevel is. It only contains 1 orbital that can hold 2 electrons. Okay, so principal energy level 1 can only hold 2 electrons because all it can fit is an S sublevel. Now, how many electrons did I say the second principal energy level can hold? 8. Where does that come from? It comes from the 2 plus 6. Okay, so looking at, let me get a different color here. Principal energy level 2, this can hold both a p and an s orbital. So since p orbitals can hold 6, s can hold 2, combine those, we can hold 8 electrons total in our second energy level. Every level you go up, you add another orbital shape for at least the first few. So now we move on to the third. This is where we start to introduce the D sublevel, which can hold 10. Now, what's 10 plus 6 plus 2? 18. How many can the third level hold? 18. So this is where these numbers are coming from. And then lastly, we won't go any higher than 4. We have an F orbital that can hold 14. We will mostly be talking about SP and D orbitals, okay? Any questions right now? Okay. Does it just feel really weird right now, right? It's just kind of odd. Okay, we'll get there. We'll get there. Now, you can write sublevel configurations based on the filling pattern. We're not going to get into where things start to get weird till later. We'll stay simple for now. So how you're going to fill till later is you are just going to follow this chart from top to bottom. So what I mean is, let's start with beryllium. I'm going to erase some of this just so it's a little cleaner. Beryllium has how many electrons? 4. Our shell configuration, we decided there's 2 in the first energy level and 2 in the second, right? That's what we're telling by 2/2. Okay. How we get there is if we write the sublevel configuration. Now we're going to incorporate these S's and P's and B's and etc. So you start with 1 S. So we're going to say we have principal energy level 1. There's an S orbital there. How many electrons can it hold? 2. So we're going to fill that one up completely first. Now we're going to move on. We're going to go to the second principal energy level. Now this one can hold 8 total, but do we have 8 electrons to put in there? No. So we're going to say, okay, we're going to go to the 2s orbital and put our last 2 in there. All right, so that's sublevel is telling us what letter S, P, D, or F it's in, where the principal or the shell configuration just tells us how many in that whole energy level. Any questions about this one so far? Okay. Let's hop to the one below, nitrogen. So our sublevel configuration, we have 7 electrons. So we're going to start again from that same spot. We're going to start with 1 S and put 2 electrons in there and write 1 S2. Then we're going to move down, go to 2 S2. How many electrons do we have left to place? 3, right? So we're just going to keep going down. The next one we're grabbing is the 2p. All right. So you have to grab every orbital in that energy level before you move on. So 2p, and then we're just going to put those last 3 in there. Sorry, I should write with green here. There we go. Okay. Does this match the shell configuration? It doesn't. This was a typo I made last year. So seeing who's on their toes. What should it be? 2, 5. Okay. So this is a typo. So I want you to correct this to 2, 5. So thinking about it, this is the first energy level and this is the second. Where does the 5 come from? 2 + 3 = 5. I know that's the hard part. All right, so this is where the 5 is coming from, because both of these, even though they're different sublevels, they're both in the second principal energy level. So pretty much anything with the same coefficient out front gets added up together to go in their digit in the shell configuration, okay? All right, next one, aluminum. I don't think this shell, I think some of these shell configurations got a little crazy, but we'll start at the sublevels, okay? So you're gonna start to see this pattern and you're gonna get sick of it. So the first one being 1s2. So make sure we're also writing those, how many electrons in there as a exponent. So we have 1s2. That's the first one. What's the next one? 2s2. All right, so far we've used up 4 out of the 13. We have 9 more electrons to place. So what does that mean for the next one? Exactly, 2p6, 3s2, and then 3p1. So it's not the most riveting thing, yes.
Why don't we have to rewrite all the 2s2?
Because there starts to be issues as we get a higher energy, and you have to know which level it is because they start to switch order. Yeah, we'll get there later. We'll get there later. Don't worry. Okay, so what should this shell configuration be then? 2, What? 8, 3. All right. I don't know what Miss Murphy was doing this day. Must have been nervous for first week of class or something. All right. Lastly, we start again, 1s2. So we pretty much can copy everything from aluminum, except we're going to add some more, right? So again, we're just grabbing from this table 1s2 and just writing it in a slightly different format. 2s2, 2s2. Then we're going to go to 2p6. Right now we're sitting at 10 electrons. We have 6 more to place. 3s2. And then lastly, 3p3. So what is the shell configuration for this one then? 5? 6. I put 3 instead of 4. Come on, guys. You'll be firm on the shell configuration, but yet you won't tell me why that is, you goofballs. All right. Any questions about this? Yeah. Is it Friday yet? Okay. Gosh, at this rate, I'm worried about lab. Okay. Orbital box diagrams. So this now is a visual way to represent what we're talking about, okay? So now we're gonna go into orbitals. The nice thing is an orbital can only ever hold 2 electrons. That does not change. The number of orbitals in the sublevels is different. Okay. So we'll get there in a second here. Actually, you know what? That might not even be a bad thing to talk. Okay, okay, I'm processing. So orbital box diagrams, they tell you how many electrons in each orbital. They tell you the electron spin. So we can have electrons that spin up and spin down, and they come together in pairs. So the maximum number of electrons in each orbital we have is 2. So the number of orbitals is just half the amount of electrons we have. So in something like sulfur, how many orbitals will sulfur have then? 8. So if each orbital can hold 2 and sulfur has 16, 8. So you can just half how many electrons you have to figure out how many orbitals you will have as well. So when we talk about spin, we designate it by arrows. So if we have something spin up, we draw an up arrow. Spin down will be a down arrow. Now, a lot of times you might see what are called fish hook arrows. What those look like is there's only, so I'm putting them in parentheses. There's only one arm of the arrow. It's like, because as you start writing these diagrams, you're going to get so sick of drawing arrows that I'm okay, as long as you're not just putting straight lines, because if I can't tell which way it's spinning, no bueno. All right. So, how is it saved? I think so. Okay, so this is how I draw my arrows. Okay. Or I go, or technically this is how I do an orbital diagram. Versus, it's a lot quicker in my opinion. Did I see a question? Okay, maybe a little stretch. Oops, I was supposed to erase. Anyway, okay, so let's say you get to something like chlorine. Chlorine has 17 electrons. That means you're just gonna have one lone electron in an orbital. So if you only have one electron, just make it spin up. And so there is a certain fill order we do. And this is that you have to fill empty orbital boxes with one electron before you start putting 2. So there's lots of rules where we'll talk about Pauli exclusion rule. Yeah, so we're gonna do this next, right here, next page. We got this. So We're bringing back the sublevel configurations that we just figured out. And now we're just going to visually represent those. So how we're going to draw an orbital is as a box. So this is an orbital. We're going to give it a name. This is the 1s orbital. The other orbital we're going to have then is what? 2s. And then how we're going to represent our electrons, we know we have 2 electrons, and each of these orbitals is an up and a down arrow. That is an orbital box diagram for beryllium. How do you spell beryllium? Just kidding. You guys already took your quiz. All right. I love it. It's just like little zombies out here. All right. Let's try nitrogen then. So now we're adding this new sublevel. We have the p sublevel. Does anyone remember how many electrons a p sublevel can hold? 6. So if a p sublevel can hold 6 electrons, how many orbitals do you think makes up a p sublevel? 3. Okay, I know lots of jargon here. So how we're gonna draw this is we're gonna start with one box. This will be our 1s. We also have our 2s, but this is how you draw a p sublevel. It has 3 orbitals. I'm gonna make those a little spaced out better. Yeah, so technically this would be 1, 2, 3 different orbitals.
2s had 2 energy levels, so why did we give it 2s?
2s is in the second principal energy level. So that it's a sublevel in the second principal energy level, but that sublevel, no matter what energy level it's in, will only ever hold 2 electrons. So I know it's weird. Okay, so now putting P-U-T-T-I-N-G, not P-U-D-D-I-N-G, putting the electrons in here, we have 2 electrons. So I'm showing you the fishhook method here. 1, 2 here, 2 electrons here. But now this is that rule. You have to put 1 electron in every box before you come back and add a second one. And how we put a single electron is always spin up. So how you represent 2p3 is a spin up electron in every orbital. Okay. So this is a special rule. Any questions about that? So if I were to cut this class in half, do you guys think you'd sit as close to each other? Same reason. They don't have to be together unless they don't want to be together unless they have to be together. This is kind of the idea behind it. All right. Next one here. So now we have quite a bit of orbitals to draw. We have a 1s. We have a 2s. 2p. So you guys can practice try to draw these on your own if you want to make sure it matches with mine. 3s and a 3p. So I want you guys to try to practice putting electrons in there. I'll see if we get the same thing. So what we got? Awesome. So everything has a buddy except the 1 loner and 3p sublevel. So sad. All right, last one here. Lots of drawing for us. We are going to have the same exact orbitals. We have a 1s, a 2s, a 2p, a 3s, 3p. So Bridge, we're all going to have these full because they always fill from the bottom, the lower stuff up, except now 3p4, how we show this is we still start every orbital, if they're in a sublevel, has to have one first, and then you just go back to the first one and draw a partner. So this is how you represent 3p4. If we had 3p5, we would add another one here. Yeah. And yes. And then d orbitals have 5. So how, because they hold 10. So this is what a d orbital looks like. S, they have 7. But we don't really do those. Nothing. Yes. So there's the Pauli exclusion rule says that you have to put one in each box before you go back and make a partner. Is it emergency? Okay, literally like in a minute I'll be done. Okay, so now just quickly recapping valence electrons. It sounds like you guys are you've heard of these before. So just remember they're the outermost shell. Or in our case, now we're gonna call that the principal energy level. So thinking about beryllium, the outermost shell, that's energy level 2, right? That's our outermost energy level. That 2, that coefficient. How many electrons are in the outermost energy level? How many are in the energy level 2? 2. So that's how many valence electrons. What's the highest energy level of nitrogen? Also 2. How many electrons are in the second energy level? Yes, 5. So this is where the shell configuration is super helpful to see how many are in the outermost. So the reason why there's 5 is because you have to count both the s and the p orbitals when we're talking about valence electrons. So aluminum, how many we got for that? 3, exactly. The highest we got is principal energy level 3, and there's 1, 2, 3 electrons. Lastly, sulfur. Great job, guys. All right, so this determines their properties. You guys should be aware that valence electrons determine the properties. If you draw with a Lewis dot diagram, all you do is draw a symbol and start putting dots around it for however many. It's piece of cake. You guys have done this before. But the last thing I want to remind you guys is 1, look at the shell configuration. The rightmost number is how many valence electrons there are. Great, makes sense. Now, periodic table. Did you guys talk about the trend of the periodic table and how that relates to valence electrons? Okay, awesome. Column 1 has 1 valence electron. Column 2 has 2. Then you skip the transition metals because they're wacky. Hop over to boron, get 3, carbon 4, 5, 6, 7, 8. And we'll talk about a little bit about filling, but pretty much you need to know is that if I call something a group, it's a column. If I call something a period, it's a row. Okay. All right. You're good, Ella. Any questions?